Good morning, everyone. So welcome back to this lovely conference on combinatorial and algebraic enumeration. For our first speaker this morning, we're very happy to have Chris Godsil, who will be talking about moments and walks.
Thanks, Kevin, and thanks to the organisers for all the work they've done. And maybe I should introduce to Emma here, who's done a lot of the work for this conference, and we should thank her. Okay, so I guess in the spirit of this conference, I should come up with a story or two about Ian and David. Their graduate students last night were telling us how much they'd enjoyed and learnt from working with Ian and how kind they were. Now, my experience was first real experience was a little different. They fed me to Jack Edmonds, was the summary. But I was at Simon Fraser University, and at that time there was a series of combinatorial conferences that used to take place in Winnipeg in summer, organised by Rolf Stanton. And so I came across one of those, and I gave a talk, something on the line about formal power series and generating functions, and it's perfectly reasonable. Then after the talk, Ian and David came to me and said, "We'd like you to come to Waterloo and give the same talk." Now, that's quite unusual. Usually if I give a talk and someone says, "We want you to come and give a talk, please don't give that one again." But said, no, come and give a talk. And I was very new and shiny, didn't realize how unusual this is. It's the only time it's ever happened to me. So I came to Waterloo and I gave this talk. What I didn't know, but what I learned fairly quickly, was that the department was in the throes of reorganizing the first combinatorics course. And there were discussions about how to do the enumeration. And there were two sides to the discussion. There was Jack Edmonds on one side and Ian and David on the others. I don't know where the rest of the department members stood, but and so the thing I remember is I got some very brutal questioning from Jack Edmonds at the end. So that was my introduction to their kindness. So, okay, I'm going to talk about moments and walks. I had a little trouble coming up with stuff would fit to the theme of this conference, but in the spirit of the thing, I decided I could go back to some really old stuff. In fact, this goes back to the early 1990s. So this is these results belong to a period which some of my graduate students refer to as the prehistoric times, which means before they were born. Ian was talking last night about mothers and grandmothers, but so these are prehistoric results. So start with matchings. Nothing very complicated here. So a matching is a set of vertex disjoint edges in a graph. And a K matching, surprise, surprise, is a set of K vertex disjoint edges in the graph. And we want to get generating functions out of this. So we use P of X comma K to denote the number of K matchings in the graph X. And so, well, I've even worked out an example here. So for the path on 5 vertices, there's 1 0 matching by conventional rule or whatever. There are 4 edges, so there's 4 1 matchings. And if you work for a little bit, you see there are 3 2 matchings, and there's no 3 matching because a set of 3 matchings would cover 6 vertices. There's only 5 available. So you get a sequence of matching. So that's nice and concrete. Now, of course, faced with a sequence, we want to return into a generating function. Now, the generating function we use here, well, the obvious thing to do would just take P X comma K, T to the K, but we don't do that for reasons I'll explain in a moment. We put in a -1 to the K, and we use T to the N minus 2K. So in some sense, we're looking at the generating function for the vertices missed by matching. The reason for doing this convention, one reason is that if the graph X is a forest, if and only if the matching polynomial coincides with the character polynomial. Okay, so with that choice, you get this result. Now, it's worth saying a little bit about the origins that matching polynomial. It's quite interesting. There's a Riordan worked on what's called the Rook polynomial. I'll say a bit about that later on. There was a very important paper by Harman and Lieb in statistical physics on monomer-dimer systems. And then a bunch of theoretical chemists were doing work on the matching polynomial. And so there were different threads. So it turns up in a number of places. And this is it's certainly the standard normalization. Now, when you define generating functions, there's some recurrences and things we can get. So the first thing here is that the matching polynomial of the disjoint union of two graphs is the product of the matching polynomials of the components. Now, it's pretty hard to come up with a sensible graphical generating function which doesn't satisfy that. And there are a couple of recurrences here. So I call this guy is vertex deletion, and here I'm thinking in terms of edge deletion. I've got little bad pictures there. The point is that we've got a graph X, we pick a vertex A. Now think about the K matchings in the graph. There are the K matchings which don't cover A, or they're matchings in X drop A. And so they're accounted for here. Now, there are also the K matchings which do contain the vertex A. Now, since they're matchings, if they contain the vertex A, they must also cover a neighbor B of A. And so you get a sum over the neighbors. Okay, and so you get what I would call the vertex recurrence. And there's also an edge recurrence, and you can derive either one of these from the other. And well, this is nice. For example, if you try and work out the corresponding recurrences to the characteristic polynomial, you get an extra term with a square root in it, the square root of a polynomial. So, you know, your life is easier. Of course, on the other hand, computing the matching polynomial is clearly NP hard. Sorry, the characteristic polynomial is the characteristic polynomial of the adjacency matrix. Yeah. I want to apply those recurrences to a couple of special cases. So if you look at the path on n vertices, okay, and so we are going to apply both these cases. I'm using the vertex recurrence, so I'm going to pick a vertex. So I pick the first vertex in the path and apply that vertex recurrence, and it gives me this formula here that the matching polynomial for a path on n plus 1 vertices is t times the matching polynomial for a path on n vertices. Take away the matching polynomial for the path on n minus 1 vertices. And you get a similar, you get a recurrence, same form for the complete graphs. You can also get recurrences for the complete bipartite graphs and for cycles. But, so there are a number of them of this form. So these are 3-term recurrences, and these will come back to haunt us later on. They tell us something about these polynomials, which I won't go into right now. But I mentioned the Rook polynomial, which I believe is due to Riordan. There's an old book on combinatorial analysis with a chapter or two on this stuff. The way I'm going to set it up is I'm going to have a complete bipartite graph KNN. Now this can be extended to KN n plus K for some non-zero, non-negative integer K, but we'll just stick to the KNN. And the understanding is I'm going to deal with spanning subgraphs to that graph. So there'll be bipartite graphs on 2 n vertices. And the Rook polynomial is like the matching polynomial, except instead of an n minus 2k, you've got an n minus k. So it's, you know, just that this is just the matching polynomial restricted to bipartite graph. And there is your most baby example. If I take the 4 matching, then its Rook polynomial is just t minus 1 to the 4th. Okay, we'll go on from there. Now, there's one little moral in all this is just because something you're interested in is NP hard to compute doesn't mean that it can't have interesting properties. And so one of the more spectacular examples of this is a formula for the number of perfect matchings. That's what that PM is doing of the complement of X. And so there's a formula for you. Okay. Now, some of you realize that we're playing with the normal density here. Okay, but we have an explicit formula for the number of matchings in the complement. Now, the proof, actually, once it occurs to you to write that down, it's not too hard. In fact, there are 2 steps. The first step is to prove it for the case where X is the empty graph, just vertices, no edges. In that case, you're just computing the moments of the normal distribution. And so it's integration by parts. And fortunately, I'm not asked to do that sort of thing anymore. So, but we have the answer. So we know that the moments of the normal distribution are given by the double factorials. Okay, and then we just use the edge deletion, recurrence, and induction, and so we get this result. Now, that's pretty. I won't go into the applications of this. Brendan McKay and I use it to get asymptotics for the number of cobariant Latin rectangles many years ago, but I want to work with the Rook polynomial version. So in this case, I'm going to think of a bipartite complement. So I've got a bipartite graph KNN, I've got a spanning subgraph X, and I'm taking the edges not in X. And that's, I'm calling that X tilde. And so instead of the normal distribution, you get the exponential distribution. And you can do much the same proof. In this case, the integration by parts is a little easier. For the empty graph, it's n factorial. And so we get that. Now, the point about these formulas is, as I hinted already, you can use them for asymptotics. And so I want to talk about derangements. Now, this is not an excuse to talk about some of the features of my colleagues. These are the derangements, permutations with no fixed points. Okay. Well, the point is that given that formula for the Rook, this integral formula here, given this, I can see the number of derangements is just the number of perfect matchings in the bipartite complement of n disjoint edges. Okay, so I can use my integral formula, and this is not too much of a stress on my calculus. So I get the first line here. I just get the dn is given by that integral. So actually, I've never actually taught a calculus course, and it shows sometimes. So we do a substitution and split the integral in two parts. One part is the integral from, so I make the substitution t equals u plus 1. So I'm integrating over -1 to infinity. So I break it in two parts, -1 to 0 and 0 to infinity. Now the 0 to infinity is just either -1 times the nth moment of the exponential distribution, or times the integral of u to the n e to the minus u from 0 to infinity. That's n factorial. So that part is n factorial on e. The other part, you need to think about it a bit and scribble a little bit, but you realize very quickly that it's less than 1. And in fact, you can show the absolute value is less than 1 plus n plus 1. So you conclude the number of derangements is the integer nearest to n factorial on e. Okay, and you didn't do any inclusion exclusion. Now it's not clear whether your students would be happy you didn't use inclusion exclusion or be unhappy that you're using integrals, but you probably lose either way. So these formulas are useful as well as being pretty. Now I wrote down recurrences for the matching polynomial of the paths and the complete graphs. And there are examples of 3-term recurrences. You've got one term on the left on n plus 1 and an n term and an n minus 1 on the right. So it's a 3-term recurrence. And some of you will realize that if somebody starts talking about 3-term recurrence, in a few moments, they're going to start threatening you with orthogonal polynomials because they're standard. Okay. And so the point is that because of these integrals, in fact, we can see that we're dealing with orthogonal polynomials in some case, a number of interesting cases. So the simplest way to, so my inner product, I'm going to be working with inner products fairly frequently. So I'm going to just use P comma Q angle brackets for the inner product. And it's just the integral with respect to some measure of P of t, Q of t, okay, over the domain of the measure. And well, so as a baby example, I've decided, what if I look at the product of the matching polynomial for Km, the complete graph and M vertices with the matching polynomial for Kn? Well, I mean, if you try to actually do this by integration, this would be a complete nut of mess. I mean, I can give you the formulas for the coefficients of the matching polynomial, the complete graph, but you wouldn't really enjoy the experience. But we don't have to do that. We're graph theorists, and we know the answer is going to be the number of perfect matchings in the complement of the disjoint union of Km and Kn. And that is just a complete bipartite graph, Km comma n. And if m is not equal to n, it has no perfect matchings, and the integral is 0. And if m is equal to n, it's n factorial. So what this integral has told us is that the matching polynomials for the complete graphs are orthogonal relative to this inner product. Okay, now this is all standard because the matching polynomials for the complete graphs are probably better known as the Hermite polynomials. So they turn up all over the place. And so, well, this you can view as a proof that the matching polynomial is the Hermite polynomial. if you use the Rook polynomials, you get another family of orthogonal polynomials called the Laguerre polynomials. And in fact, so that's using KNN. If you use KNN plus A, you get what's called generalized Laguerre polynomials, but I won't bother with that. And I had the 3-term recurrence for the path and n vertices. That's telling us, once you look at the initial conditions, that you're dealing with a Chebyshev polynomial. Now, there are two kinds of Chebyshev polynomials, one with the T and one with the U, and I always get them mixed up, and I'm not going to try and separate them now. And also, there's a bit of scaling going on. When you're dealing with orthogonal polynomials, you get to choose a scaling, and so you might want to say they're orthogonal polynomials. It should have norm 1. Well, don't do that. That makes your life miserable. What I'm going to be doing is just making them monic. So for the combinatorial purposes, that seems to be the most convenient choice. So when I say this is the Chebyshev polynomial, I may have to scale it a little bit, for example. Okay. Ian's not looking too puzzled, which reminds me, Ian's, of course, well known for being able to keep a straight face. He's very hard to read, even without the mask. My favorite story here was many years ago, we were interviewing candidates for a position, and Ian and I went to the grad club for lunch with one of them. And so we're sitting there with a perfectly nice lunch. And then, okay, so there's a candidate, Ian, the department chair, and me, who was currently the graduate chair. This candidate launches into a 5-minute rant about, couldn't understand why people went into administration. It seems to waste time. Why would anybody possibly do it? Went on for some time. And Ian didn't bat an eye. All I'll say is, if you're in a situation where you still have to be applying for positions and interviewing, don't view that as a role model. So I've got my inner products and I've got my various polynomials. So my point of view of this thing is that we have these matching polynomials, and a number of them turn out to be interesting families of orthogonal polynomials. And so they're orthogonal with respect to some density, and densities have moments, just like lectures, except then the moments all have the same length in some sense, but not in lectures. So we'll come back to that. So if you have a probability density, the moments are just the integrals of the powers of x. So okay, so there's no surprise there. And there's the moment generating, what they call a moment generating function, which is an exponential generating function. That's exactly what I want, as it turns out. So, so the point here is, whenever somebody gives you a measure, then you can, if you choose to, write down the moments. And under fairly weak conditions, the moments determine the distribution, and so they're quite useful in practice. And of course, when you're doing statistics, you care about the first moment and the second moment, and you try and ignore the rest of them. So we've got the moments. Now the point is, how do we get in general? How do you get a family of orthogonal polynomials? Well, you start with the powers of variable t in this case, okay, and that's a basis for the vector space of polynomials. And now we want an orthonormal basis. Well, what do you do if you want an orthonormal basis? We tell the kiddies you use Gram-Schmidt. So you apply Gram-Schmidt to this sequence of polynomials, 1t, t squared, until you get a sequence of orthogonal polynomials. Now you have to choose how to scale them, and as I said, I'm going to scale them so that they're monic. Okay, I get this sequence of orthogonal polynomials. So the point is, when I'm doing the calculations to get these polynomials, all I need are them from the distribution or density are its moments. Everything, once I have that, I can do the polynomials. It's not the most pleasant way of getting the orthogonal polynomials, but you can do it. So as I'm saying here, everything is determined by the values of the moments. And we saw that, well, when I started with the integral formula for number of perfect matchings in the complement graph, okay, the moments turn up there. When I look at the empty graph, I'm looking at the moments for normal distribution. So the question is, what this is telling me is that there are sequences of moments which have interesting combinatorial interpretations. Okay, and so I want to think more about that. Well, I talked about 3 terms of recurrence before, but it's probably time to get a little more explicit. So I need a couple of observations. This is the closest I can get to a proof, I think, here. If I have a polynomial Q of degree less than n, and I have the nth orthogonal polynomial P sub n, then Q and P are orthogonal. Pn is orthogonal to all the polynomials of degree less than n by construction from the Gram-Schmidt. Okay, so that's sort of fact number one. The other point is that, well, technically the statement here is that multiplication by t is a self-adjoint operator on polynomials with respect to this inner product. Now, let's not be silly. All it means is that t of p comma q is equal to p of t comma p comma tq. So we can move the t backwards and forwards without paying any prices. Now, what happens here then, if I'm dealing with orthogonal polynomials, t times pn is a polynomial degree n plus 1. Okay, and so if m is greater than n plus 1, this is 0. What's going on here? I've lost my, here we are. So, and on the other hand, if m is less than or equal to n minus 2, then this is 0. So what that's telling me is that Tpn is orthogonal to all the things with large index and all things with small index. In fact, it must be a linear combination of Pn plus 1, Pn, and Pn minus 1. And that's my three-term recurrence. Okay. So, and so this is a proof that every sequence of orthogonal polynomials will satisfy a three-term recurrence. Now, I'm going to write my three-term recurrence in this form here. It's important that, in fact, Bn will always be positive. And the nice thing is that if you've got this recurrence, we can convert this to a matrix. And so given the recurrence, I can write down this tridiagonal matrix, and it could be infinite. In fact, it's not going to matter. The thing is, if you take the leading k by k block of that matrix and take each character polynomial, that is your kth orthogonal polynomial. And this is just an easy consequence of the three-term recurrence. So you can get the polynomials as characteristic polynomials of segments of this matrix. And so this tridiagonal matrix gives you orthogonal polynomials. Okay, and that's interesting because what's going to happen in the examples we care about, the bn's will be non-negative integers and the a's will be non-negative integers. And so from my point of view, you're staring at a weighted path. Now you might say it's not symmetric, but that can be fudged, so I'm not going to fuss about that. And so I got two examples here. For the path on n vertices, the tridiagonal matrix is just the adjacency matrix of the path. No problem. That's not a given or anything. And for the Hermite polynomials, for the matching polynomials, the complete graphs, you get that matrix there. So you have 1, 2, 3, 4 on the superdiagonal. So okay, so and just for variety, there are lots of probability densities. If you suffer through a number of stats and probability courses like I did, you realize there's more than just the normal distribution. And the common one, of course, is the Poisson density. And I've given the definition here. And so that gives you a tridiagonal matrix. In this case, you've got 1, 2, 3, 4 still on the superdiagonal. The diagonal terms are just increasing integers. And so you get there's a sequence of orthogonal polynomials. I think I've written it there called the CAE polynomials. Now, these are not matching polynomials, but they, I'm not just interested in matching polynomials. We're trying to study sequences that are combinatorially interesting. And so, for example, the moments of the Poisson density are the Bell numbers, the number of partitions of a set. And so that's as combinatorial as you would hope to get. And so actually I was googling around a bit. It's surprisingly hard to get basic information about the CAE polynomials. They basically say this can be written as some hypergeometric function, and these are the asymptotics, and then they go on to talk about something else. So I went to the trouble of working out the first few. And so, as I said, the moments of the Poisson distribution of the Bell numbers, and that little triangle on the triangle here is an algorithm for computing the Bell numbers. You just you start with 2 1s. That's how you do it. You start with 2 1s, and their sum is 2, 2, 3, 5, 5, 7, 10, 15. Excuse my writing. So you get this, the Bell numbers. I was very pleased to remember that. Anyway, so we have those examples. So the summary actually at this point is that so each probability density mu, we have a number of sequences at this point. We have the moments, we have the inner product, we have orthogonal polynomials, and we have tridiagonal matrices. And the tridiagonal matrices, as I said, I'm going to view these as weighted adjacency matrices, or adjacency matrices of weighted paths. Now, you might argue that these aren't symmetric because I've got BI above diagonal 1 below, but it turns out so long you can replace that, you can change the, you can replace the 1 by the square root of BI and BI by the square root of BI. Now you have a symmetric matrix and you haven't changed the spectrum or the characteristic polynomials or anything. So it's morally symmetric. Okay, so we have this data for each probability density, and we have a number of examples where these things are combinatorially interesting. And this is summarizing what I said. I'm going to be assuming now that I'm given whatever polynomials or density I'm working with, I've got the property that this matrix, tridiagonal matrix, will have non-negative integers as entries. I can probably allow negative integers on the diagonal, but I don't care. And in the examples I'm dealing with, the diagonal entries will be non-negative. Excuse me. Now, the reason this is useful is because we now get a second interpretation for the moments. I've got this tridiagonal matrix A, and I'm assuming it's index 0, 1 up to whatever. And then the theorem is that the nth moment of the density is just the number of closed walks of length n starting at 0 on the path. So that gives you a combinatorial interpretation of the moments in terms of closed walks. Okay. That's not too hard to prove. Most of this stuff is in my book on algebraic combinatorics if you're looking for a source. But in this setup, the moment generating function, well, it's just the 0, 0 entry of the x of TA. Now, A is the adjacency matrix of a weighted path, and you might be preferring to think of that path as being finite, but there's absolutely no reason why it has to be. This is well defined and works in general. So it's just x of TA, the 0, 0 entry, that is the moment generating function for the sequence, or for the density. I need a slight generalization. So this is the, that wasn't what I wanted to do. So here's my moment generating function. There's kind of extended moment generating functions. I'm not sure if I have a name. So, well, these are the generating functions, exponential generating functions for the walks on my path, which start at 0 and finish at the vertex R. Okay, so we have a family of things. And these are related. Well, there's a formula here which relates f of t, well, f of r with the orthogonal polynomial. So f sub r is what you get when you apply PR of the operated d by dt to f of 0. So if you have f of 0 and you have the orthogonal polynomials, you can write down, in principle, you can write down the series. You write down the other terms of the rest of the terms of the series. And so these things have a number of interesting properties, and I'm just going to list one of them. You have what we call an addition theorem, so you can express f0 of s plus t in terms of fr of s and fr of t, and the formula's there. I won't say anything much. One more thing about that. The secant is a moment function of the distribution, the secant function. Okay. And so if you, this is an exercise in my book, and I'm not sure I could do it now, but you can actually verify that for the, in this case, this identity here becomes this, which should be more familiar. And that's why it's the one reason why you call it an addition function. Of course, nobody can remember the addition rules, so even for cosine, but we'll leave it at that. Now, you may think I have enough sequences and terms, but I'm going to just throw one more at you. There's another family of polynomials. So these are polynomials. Now, if I was a physicist, I could say that they're dual to the orthogonal polynomials. Now, when a physicist says dual, as far as I can tell, what that means, if you look at it in the right light, there's some vague relation between these two things, but nobody can explain it. Mathematicians usually have a more precise meaning in mind. But the idea is simple enough that we've got the orthogonal polynomials. I got the orthogonal polynomials by starting with a basis for all polynomials, the powers of t, and use Gram-Schmidt, and then I get a second basis. And so the innocent question you ask is, okay, so we have formulas for orthogonal polynomials. We can write the orthogonal polynomials as linear combinations of the first basis, the powers of t. Okay, so what about doing the reverse process? So I take the powers of t and write those as linear combinations of the orthogonal polynomials. Now, the thing that may be interested in this is the observation that for the Hermite polynomials and the Laguerre polynomials, the matching polynomials are complete graphs and bipartite graphs, complete bipartite graphs. When you do this process, you get the same coefficients up to sign. Okay, so I'll make this more explicit. So here so I want to express t to the n as a linear combination of my orthogonal polynomials, and so this is just a standard Gram-Schmidt in your first course in linear algebra. This is the formula you would use. You compute the inner product of p to the n with t to the n, normalize it, and so you get what I'm calling the inverse polynomial. Okay, and so for the Hermite polynomial, p starred, well, it looks a bit of a mess, but all you're doing is throwing away the signs. This is what you have to do, throw away the signs. So you take the matching polynomial complete graph, delete all the signs, and you're staring at the inverse polynomial. And for Chebyshev, now you can work out, I'm using the cycle here, the matching polynomial with a cycle is also, it's the second Chebyshev polynomial. In fact, it's the first one as a rule. Now, and so in that case, I mean, you can work out the coefficients of that. It's an interesting exercise, but the inverse polynomial is a lot simpler. It's just binomial coefficients up to half n. So, you know, so there's something going on there. And in fact, there's a combinatorial interpretation. Since it's a polynomial with non-negative coefficients, it ought to be a generating function. And it is. A generating function for the walks on my path of length n, that's my weighted by the height, how far they get to the right. So we get interesting generating functions. How am I going for time? Fine. So our summary then is that we have all this structure attached to any probability density. And so the moments, inner product, orthogonal polynomials, the tridiagonal matrix, now we have the inverse polynomials. And that's as bad as it gets. Yeah. Okay, so time's all right. So there's a feature of this room which worries me. I have this nightmare where I've died and gone to hell, as may seem appropriate, and the devil's taking me my place of appointed punishment. And it turns out it's a lecture room. And there's somebody at the front rabbiting on about some tedious problem in point set topology. I hope there's no point set topologists here. And so I sit there and I say, well, you know, what is this hell? What's going on? And the devil says, look, there's no clock. Just like this room. So now I should have Ian and Kevin worried. So as I said, the stuff being talked up now, you know, is fun, but it's old stuff. I did it a long while ago. It was 30 years ago, roughly speaking. The interesting thing from my point of view was I was thinking about this recently, and I realized that it actually interacts with something I've been looking at more closely in recent years, in particular, continuous quantum walks or quantum walks on graphs. So I've had an interest in quantum walks for some time now. And so let me talk a little bit about that. So I'm not going to go into any physics. The best way of thinking about a quantum walk is kind of a black box. Okay, you feed in a graph and you give it an initial vertex. So you're thinking of it as a walk. Okay, and then you press go and let it run for a certain time. And then you press stop, and the output is a vertex of the graph. Now, if you do the same thing again at a different time, you'll probably get a different vertex. So what you see at time t is a probability distribution on the vertices of the graph. It's telling you the probability that you observe a particular vertex. So it's a simple black box. I mean, there's a lot of grant money going into this and a lot of waffle, but there's just a little black box. And I said, you stuff in the initial vertex, you stuff in the graph and let it run. And if you get bored with using the adjacency matrix, which is what I'm using here, you could use the Laplacian or the sinus Laplacian, but let's not go into that. So it's simple enough. And so the problem is to answer questions about the probability density you observe at certain times. Okay, I mean, the result of a measurement in quantum physics is always a probability density, although the physicists get unhappy when I say that for some reason. But that's, so we're fine there. So that's all the physics you need to know. Now, the quantum walks are useful as, potentially useful, I guess, as subroutines in quantum computation. And so there's a large literature. One thing that you can do with quantum walks is you can actually allows you to copy the state of a qubit. Now, the problem in quantum computing is you can't copy a state. There's no linear function which takes a state to the tensor product of the state with itself. I mean, that map is not linear. And in quantum mechanics, all maps have to be linear. And this is called the no cloning theorem. And you can find proofs that go over several pages. But basically, it's just the fact that the map that takes X to X tensor X is not linear. Okay, so you can't copy states, but with a quantum walk, you can sometimes, if you're lucky, if the graph's got the right properties and you stop at just the right time, you can arrange that the state of the qubit I, let's say qubit J at time t, is identical to the state of the initial qubit at time 0. So it could allow you to copy. Now, the bad news is that it's rather difficult to arrange. And so there's only finitely many connected graphs with maximum bouncy k on which this happens. So it's not trivial and it's somewhat rare. And so this is the question I'm asking here. So I stated well, I should define this, I guess. So the behavior is determined by this matrix function u of t, the exponential of ITA. Now, physicists will put in minus I, and I should too, but I get signs wrong, and it doesn't matter to anything you do, so I leave it off. So we have x of ITA. So A, as I said, is the adjacency matrix of graph. And for the moment, you can think of this as a finite graph, but it's going to be an infinite weighted path before very long, of course. So the probability that at time t we observe state j, given that we start at I, is given by the jth entry of the ith column of u of t. Okay, and so that column is giving us all the information that you can get by experiment from the system. So questions about the entries of u of t are not physical. There's nothing you can do in physics which will tell you what the entry of u of t is. You get the squares of the absolute values. Not that that's going to matter too much. So the problem is trying to arrange things so this is equal to 1. Actually, I don't think I need that. Well, the other point, of course, is I'm looking at x by TA, and it only took 30 years, dawn on me. Well, this is exactly what I was looking at when I was looking at these moment sequences and things, except there was x for TA. Putting in I can't change things too much. Well, that's just nonsense. That's like saying if you understand the hyperbolic functions hyperbolic sine and cosine, you understand Fourier series. But I mean, you're just putting in an I. Actually, I'll skip that, I think. So as I said, I can, and I don't have to take my graph to be finite, so I can take A to be one of my triagonal matrices. And it turns out you get some interesting behavior here, so that I can actually describe the outcome. So the simplest case is just to think of it one-way infinite path, and you're having your continuous quantum walk on that, and so you're asking about these probabilities on that walk. Okay, and so for that I would take A to be 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, so on, and I can have an explicit formula, and the point is that well, you get more than an explicit formula, you get a known function. That x of ITA, the 0, 0 entry of x of ITA is a Bessel function of the first kind. And so any information about Bessel functions, and there are huge books on the stuff, can in principle give information about this walk. And so it tells you, for example, if you're thinking about a continuous walk on a one-way infinite path, then, okay, it's given by a Bessel function. The theory tells you, for example, that the probability of being on your starting vertex is zero infinitely often. In fact, the gap between the intervals where zero occurs is more asymptotic to a constant time, something like 4 pi. So it's zero infinitely often. This is kind of interesting because if you look at a finite path, that is not what you observe. And that's interesting. Well, I find that interesting because the physicists they say, I'm going to work with this infinite path. And you can ask snarky questions about what their state space is, what Hilbert space they're using, which they'll prefer not to answer. And then you say, well, but you can't. I'll say you can't possibly implement an infinite path on the real world. And they say, oh yeah, we just take a finite path as a good approximation. Well, it's only true up to a sense. If you run the path, if you run things for a long time, the behavior on a finite path is completely different to the behavior on an infinite path. Okay. And I'll just finish with a couple more examples. If you work with the complete graphs, then the moment generating function you get is x e to minus t squared on 2. Now that is now the 0, 0 entry of my transition matrix. So that's just given by an exponential. And if you were to use the Charlier polynomials, you get exponential of e to the it minus 1, which is a periodic function, which is again quite different from what you'd normally see. In fact, well, we don't care too much. There's a question you can ask here is, it's actually quite, this is sort of the limit of my abilities. As my dentist wants to remind me. Sorry. Yeah, I was using the iPad for a lecture once and my daughter decided to Skype with me during the lecture. I was asking before, I'm interested in the cases where the entries of u of t have absolute value 1. It's also begun to interest. And now, if an entry of u of t has absolute value 1, all the other entries in that row and column are 0. And so it's natural to start thinking about when these things can be 0. And by and large, we can't do much damage to that question. And so, for example, I'm not sure, though it might be solvable. If I look at the path of 5 vertices and ask, I start on vertex 0, I'm asking what's the probability on vertex 4, and I want to know, is that ever 0? Now, I know there's going to be arbitrarily close to 0 infinitely often because I'm dealing with almost periodic functions, but I can't tell whether it's 0 or not. And so the example with the infinite path is interesting because you are getting zeros at regular intervals. And so there's some questions there, but I will stop at this point. Thanks for your attention.
Okay, we should have time for 1 or 2 quick questions. Well, I have a question. Does any of this machinery give you any new insight into doing algebraic manipulations with tridiagonal matrices, such as determinants or logarithms or something like that?
The easiest answer, I don't know. I mean, it's not important. I mean, I guess the determinants are straightforward because the determinants sort of hidden in the orthogonal polynomials anyway. It's just a constant term essentially. So, so you have that, and so the magic words here are Sheffer sequences, which you may have come across. You didn't repeat the question.
Oh, I think people can hear me.
Yeah.
Any other questions? Anything online? Okay, in that case, let's thank Chris again.